Hi there, Level 2s. So we're going to look at motion. But just before we do, I have a good surprise for you. Ta-da! That's the surprise. I got a new microphone. So hopefully this one will work better for you and you'll be able to hear a little bit better. This chapter on motion is chapter 8 in Housden, and I'll divide it up into 3 lessons. So this is the first one. Here goes. Just thinking about velocity and speed, let's do this example. So Apollo 11, the first spacecraft to land people on the moon, took 102 hours to reach the moon. The average speed of the craft was 5,500 kilometers per hour. So stop right here and have a quick think about how you would calculate what was the distance to the moon. So distance is speed times time, and the speed you already know is 5,500 kilometers times by the 102 hours that it took. You can cancel the units and you'll end up with 561,000 kilometers. So just comparing speed, which is what was in the previous question, and velocity. So velocity is the vector quantity, whereas speed is the scalar quantity. So velocity has got both the magnitude, which is the speed, and the direction. Okay, and it's calculated by the change in displacement divided by the time taken. So now remember that both displacement and distance have got the symbol d, whereas distance is a scalar quantity because it only involves magnitude or size and not direction, whereas displacement is the vector quantity. We've done this in the previous chapter. Good. Velocity is measured in meters per second to the minus 1. And we write it that way, always. And delta D, which is displacement, a change in displacement is measured in meters. Delta T, or the change in time, is measured in seconds. So we've said before, the motion of an object is described using these vector quantities: displacement, velocity, and acceleration. We've discussed the first two. So the third one, acceleration, is the change in velocity per unit time. So this means when an object speeds up or slows down or changes direction, it is accelerating. Okay? And that means you've got to calculate acceleration using the change in velocity over the time taken for that change to occur. It's measured in meters per second to the minus 2, or meters per second squared. Right, here's an example. A car travels 6 kilometers north in 4 minutes and then 8 kilometers east in 5 minutes. So to find the displacement, we would need to look for the resultant vector. In other words, on the diagram that would look like that across there. So we've added these vectors head to tail method, and we've found the resultant, the 10 kilometers, which is the displacement. Okay, we could also have done the calculation this way. 6 squared plus 8 squared gives me 100 square rooted, gives me 10 kilometers, converted into SI units, which is 10,000 meters. To find the angle, as shown in the diagram, I should have drawn a theta in here, but never mind. So opposite over adjacent, opposite over adjacent, for that angle is 8 over 6, which is tan theta, and then rearrange to find the inverse of tan. And the angle becomes, what we've solved is 53 degrees. So that is the angle here. So we write the statement: displacement is 10,000 meters at a bearing of 053 degrees. So remember, bearing is from north in the clockwise direction. So anyway, from north. Right, the next part of the question, to find the average velocity, we work out the change in displacement over change in time. We first find time in seconds, so 9 minutes in seconds is 540 seconds. We then substitute these values in meters and seconds into our equation, and we come up with 18.5 meters per second. Now, to calculate the average speed, slightly different because the speed is the distance divided by time, not the displacement divided by time. So the total distance covered is 6 plus 8, which is 14 kilometers. Converted to meters is 14,000 meters, divided by the time of 9 minutes, which is 540 seconds. And so we end up getting a different value for the speed. And you can see here that there is a difference. Now, acceleration is a vector quantity. As I've said before, it is the change in velocity per unit time. And we've discussed this already. It's measured in meters per second squared. One thing that you will need to work with quite a lot, and we will go over this again, but acceleration due to gravity near the surface of the Earth is 9.8 meters per second squared. Now that value, it means that if you dropped an object out of an aeroplane, that it would accelerate at 9.8 meters per second. So at the end of 1 second, it will be traveling at a velocity of 9.8 meters per second. At the end of the second, so at the end of 2 seconds, it will be traveling at 9.8 plus 9.8 meters per second, which is 19.6 meters per second. That will be its velocity. So for every second that it falls, it speeds up by 9.8 meters per second. Right? And that is slightly different on the moon, in that on the moon, it's only 1.63 meters per second squared. So the acceleration due to gravity is about 1/6 the value that it is on the surface of the Earth. Here's another example. For using acceleration. So a car starts moving from rest at a stop sign. It accelerates at 1.5 meters per second. Find the speed of the car after 7 seconds. So we can use acceleration as change in velocity over change in time. Rearrange that to give us velocity equals acceleration times by time. What are the little arrows on here? Remember, that just indicates that these are vector quantities. And so we end up with velocity is 10.5 meters per second to the -1. Just want to point out here very quickly again, make sure you write down the equation, then substitute in the correct values in the SI units. That you don't need to put units into the substitution, but you definitely need an answer with units. Okay, so tackle every problem like that. Next question, after how many seconds is the car traveling at this speed? If it accelerates at 1.5. So again, you take this equation, rearrange it. T is equal to V over A, velocity of acceleration, and you end up with 12 seconds. So at 12 seconds, it will be traveling at that velocity. And the last question, if the car is traveling at 20 meters per second and comes to a stop in 5 seconds, what is the braking deceleration? So it's the final velocity, so it comes to a stop, minus the initial velocity, which is what it was traveling at, over the time taken for that change. And you end up with -4 meters per second. So remember, negative value like that shows that an object is slowed down. So the change in speed is negative. So therefore, so is the acceleration. So we use words like deceleration or retardation, which also describe negative acceleration. Work through the examples on page 92, 93, 94 in class, and then complete activity 8A on page 98. Adios!